chorus going on in the hall from the class act group. Hopefully they will serenade us levelly as we go on here. So I'm back at test hint number 19. Describe how hydrogen bonding affects water molecules. And I had a chance to draw several water molecules here, and you'll notice that they're lining up in a particular way. And that is such that there's an attraction between the hydrogen on one molecule and the unshared pair of electrons on another molecule. And that happens in many different places, and water will build up a crystal from that. If it solidifies and forms ice, it will also build up or come together in drops because of that attraction. And we don't see it on our model kit too well because we don't see the unshared pairs there. But there is this nice attraction that gives water all the wondrous properties that water has. Test hint number 20. Identify the number of extra valence electrons in the Lewis structure of a specific polyatomic ion. Okay, when it comes to extra valence electrons, we're talking about that whole molecule as a group. In your second covalent molecules lab, you actually drew the structures of several polyatomic ions. And one of the simpler ones is, let's see, how about phosphate? We'll do phosphate. Phosphate is phosphorus with 4 oxygens attached. And we'd have, oxygens, not hydrogens. We consider the 5 valence electrons on phosphorus, and those would be a unshared pair, and then clearly 3 shared pairs. Each of these oxygens is going to end up with 6 valence electrons, 3 unshared pairs on the outside, and then this unshared pair actually formed a coordinate covalent bond with one of the oxygen atoms. But if we count up the number of valence electrons compared to the protons, we're going to be over by a few. And that is because we actually have 3 additional electrons in this ion. This ion has a -3 charge. So when we're asked how many extra valence electrons, well, it's 3. It's the same as the charge. What would it be in hydroxide, which has OH minus? Well, there'd be 1 extra valence electron there. So that one should be pretty straightforward. Go back and think about the polyatomic ions that you've drawn. Take a look at the pencast that I have posted. There's a couple different ones that show you how to draw some of those ions as well. Test hint number 21. Use VSEPR to describe the shape of a specific molecule. Well, every time I've been asking you to describe the shapes in lab, you've been using valence shell electron pair repulsion theory to do that. Remember, John calls it repulsion. They're waving. They're waving as they're wandering off and serenading here. So here is a methane molecule. This is tetrahedral. This is the best example of tetrahedral geometry, the simplest, where we have 4 pairs of electrons that are shared and move as far apart from each other as they possibly can be, 109.5 degrees. We could have a bent molecule like water. We could have a linear molecule like carbon dioxide. We could have another tetrahedral molecule like H2Cl2, again tetrahedral. Or we could have something that's trigonopyramidal. I didn't happen to grab one of those and put that together ahead of time. You should know the basic and general shapes. Now, I'm not going to throw in there octahedral or trigonobipyramidal or something that's, T-shaped planar, something that's really weird like that, which even though they aren't all that weird, we're going to stick with the basics. You should definitely know the most common geometries. All right, test hint number 22. Explain how VSEPR affects the shape of molecules. Well, I alluded to that already. Our basic shapes happen because shared pairs of electrons and unshared pairs of electrons are pushing away from each other. Remember, electrons are negative. They're all the same charge. They're going to want to repel each other. Yes, they can be in orbitals together when they're spinning in opposite directions, but that's a magnetic attraction. And we know that the unshared pairs, say on this water molecule, are going to push the bonded pairs closer together. because the unshared pairs take up more space. You had a chance to look at that in several of the modeling examples on the simulations on Moodle. Oh, if you're just watching these the night before the test and you didn't look at those simulations and models, please get on those and do that. Take a look. There's a couple of them that let you play a little video and see the animation in 3D, and they can show the unshared pairs that I can't show you here with the ball and stick model kit. Okay? Let's see. So VSEPR, just in its most basic state, tells us, gives us a way to predict the shape of molecules. Test hint number 23. Use VSEPR to describe the shape of a specific molecule. That's what test hint 24 says as well. Use VSEPR to describe the shape of a specific molecule. I'm going to give you several questions in a row that are examples of molecules. I'll give you the molecular formula, maybe H2O for water, CCl4, something like that, and you're going to have to tell me what the shape is. So a few questions like that. Which takes us to question number 25, where the test hint says, define hybridization. Again, there's a simulation, a couple different simulations posted on Moodle that you might want to take a look at, because they can show you how things blend together with animations that my artistic ability cannot recreate here on a static whiteboard. But in hybridization, our most common kind of hybridization is sp3. And it happens typically, or most obviously, for carbon, where our 1s orbital is filled with 2 electrons, our 2s orbital has 2 electrons, and the 2p has 2 electrons. That only leaves 2 half-filled orbitals for carbon. Sorry about that. So 2 places where carbon can bond, yet carbon is our best example of tetrahedral geometry. Tetra is 4. And so carbon needs 4 places to bond. And what happens is that this 2s and the 2p orbitals actually blend together in energy. The s orbital moves up a little bit in energy, the p orbital comes down a little bit in energy, they meet in the middle, so to speak, and they form 4 hybrid orbitals that chemists, wildly creative that they are, just call sp3. sp3, that's 4 things. And the electron here moves over, so that we have 4 places where carbon can bond with other things. If hydrogen comes along with its half-filled s orbital, a hydrogen can bond here, 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 and here, and that's how we end up with this tetrahedral methane molecule.